Saxon Algebra 1, Lesson 108. I have a story to tell you about this. But first I'm going to show you something that's super obvious, and then I'll tell you the story. Let's say that we have, it's not super obvious. It's obvious to me because I've been doing this a long time. It might not be obvious to you. If we have the square root of a number and we want to get rid of that radical sign, the way we do it, I'm putting the parentheses around, but you don't always have to, is we square it. Squaring something and taking the square root of something are opposites. So if we do both, we get the plain number back, all right? This is gonna be useful in our lesson. And this is if x is greater than 0, right? Because we can't take square roots of negative numbers. Not yet anyway. We'll have imaginary numbers to help us do that next year. But for this year, this has to be a positive number. But if it is positive, then this works, right? A pig house and a square cancel each other. Yay. Okay, story time. I wrote this all out in a blog with a really elaborate illustration that I drew for one of my students a few years ago. I think it might have been Tori Bragg. That's not important, but it's fun to know. And I was defining this term, isolate the radical. Okay. So I grew up in the 60s. I was a child of the 60s. I was a little kid when the Vietnam War was happening, but we lived in a small town outside of Ann Arbor, Michigan, which is where the University of Michigan is located. Okay? Big college campus, very active in the 60s with, anti-war demonstrations and things like that. We spent a lot of time in Ann Arbor. That's where we went to the doctor. That's where we went shopping for clothes. We were there once a week or so, and we very often drove through and around the campus. We'd see all the big buildings with the granite fronts and all the columns and the steps going up. I used to be quite into, pressing my nose on the car window and just checking this out. I thought it was really interesting and cool. Well, every now and then we would see, often on the steps and the porticos of those big old-fashioned buildings, we would see groups of students gathering, and usually there would be one in the middle up near the top with a bullhorn, speaking, in a projected voice. Often there would be banners and posters and things like that. And my mom explained that those were protests that were going on. And again, I could read the signs and I knew they were like against the war or things like that. But there was usually the one person with the bullhorn who was leading it. One time when we saw a gathering like this, as we were driving by, campus police, or I don't know, maybe they were the city police, were coming up to the group, and I don't know what they were doing, but the effect of their presence was to break up the group, right? And as the police are coming up, all of the students in the crowd are scattering, right? The only one who didn't scatter was the person with the bullhorn at the top of the steps. I've drawn a picture of it in this other thing. I will link you guys to it because I can't really reproduce the whole drawing right now. But in any case, just imagine this crowd of onlookers with their posters and their, scraggly beards and their bell-bottom jeans dispersing like fish swimming away, and these police coming up, but now it's just the guy with the bullhorn, the radical, as my mom called them, the radicals. And by the police coming up, what they effectively did was they isolated the radical, right? They drove all of the fellow protesters away. And so the radical with the bullhorn was the only one left from the protest standing there, and all of his people had run off. They were usually guys. So I think of that scene whenever I hear the phrase, isolate the radical. However, when we apply it to mathematics, it's a little different than police chasing off crowds of people, leaving guys with bullhorns stranded. It looks like this. We're told to solve. Okay, the first step in this type of problem is to isolate the radical. Oh, so my story flashes through your mind. You see that the groups of people walking off, splitting, you know, to either side. Like as the police came up from the left, up the stairs kind of on the diagonal, and the crowd just, you know how the steps like that, the big granite steps are really wide, so the crowd just kind of melted away on either side. That's what we're imagining. This is our radical. And we have to isolate him, and the way we're gonna do that is we're gonna send the crowd of other protesters away to the other side of the equal sign. Okay, so this is how we isolate radicals. We identify the radical, and then we send the crowd away. So now, you have a fabulous picture in your mind whenever we go to do this, right? Okay, that was a long way to get here, but we did it, right? So now we have a situation that looks kind of like this, right? We want to get rid of this radical sign, so we do it by squaring over the top. If we do it to the left, we have to do it to the right. And so these two cancel each other, and we get x minus 2 equals 9. Oh, okay. Now we're on solid ground, right? X equals 11, and that's our answer, right? However, when we do this process of squaring to eliminate the radical, sometimes our solutions go a little wonky. Not because of any mistake we're making, but this process can sometimes create false solutions. So what we have to do, just a second, let me fix my steps. Okay, so first we isolated the radical by subtracting the 3. Then I call this squaring away the radical. We squared it away by squaring both sides. Then we just solved it, basic algebra. And now for the final step, we have to check our answer. I am not a fan of checking answers in algebra unnecessarily. I mean, we work the problem. We shouldn't have to check every answer other than in the solutions manual. But this is one where we do have to, I would say, test our answer. So what we do is before we declare this the solution, we plug it back in. Let's try it. So here's our test. It'd be the square root of 11 minus 2 plus 3 equals 0. This equals 9, right? 11 minus 2 is 9. The square root of 9 is 3. 3 plus 3 equals 0. No, that's false. So this doesn't work, and our final answer is any one of those 3. I like to put all 3. John says the empty set, but I think any of those 3 is perfectly acceptable, okay? Okay, so sometimes these problems don't work out, and I'll give you a hint. This is where our solution went bonkers. When we squared away this negative number and got the positive, that's where things went a little crazy. All right, let's try another one. There are how many? 3? Oh, there's 5. Whoa. Buckle in, you guys. We got lots to do. Let's do 108.2. Solve. Square root. X minus 2. I don't have to talk out loud. You don't need to hear that. Okay, there we have it. Once again, there's our radical. There's our crowd. We have to isolate the radical. We send the crowd running. Cancels. Square root of x minus 2 equals 6. We now square both sides to get rid of the radical. We get x minus 2 equals 36. Add 2, x equals 38. Now we test. Don't draw a box around it yet because we don't know if it's going to work. Go back to our original expression. Plug it in for x. 38 minus 2 square root minus 6 equals 0. 38 minus 2 equals 36. Square root of 36 is 6, so 6 minus 6 equals 0. This time it's true. So that is our answer. It worked this time. Yay! All right, let's make it harder. I know. Why? Why? Because This one looks a little different. We have a square. We've never had that before. Okay, well, don't let it throw you. The process is exactly the same. We isolate the radical. The cops come up. The radical stays. He runs away. Goodbye, crowd. Square root of x squared plus 9 equals 5. So we're going to square both sides. Now we get x squared plus 9, right? Because this conquers that, equals 25. Subtract 9. This is just basic algebra. X squared equals 16. Aha! Now we take the square root and we get x equals 4. All right, that went smoothly, but now we have to check it, right? So we're going to plug back into the original equation. 4 squared plus 9 minus 5 equals 0. Okay, 4 squared is 16. 16 plus 9 equals 25. Square root of 25 is 5. 5 minus 5 equals 0. But wait. When we took the square root here, it could have been minus 4 as well, right? Positive or negative. So we want to check this solution too, which makes sense because the power of our equation tells us how many answers we should have, how many roots. So since we had the square, we should be able to get 2. All right, so let's try it and let's see what happens. Minus 4 quantity squared plus 9 minus 5 equals 0. And then the same thing happens because once we square this, we get positive 16 plus 9 equals 25. Square root of 25 is 5. You see what I'm saying. So both of these work. And both are happy answers. Yay. This is a long lesson. Lots of problems. Which reminds me of my marker bag that I saw in, I think it was Urban Outfitters one time. Dear math, grow up and solve your own problems. I mean, kind of, right? But no, we have to help it out. We have to parent these math problems and help them solve themselves. They're not going to solve themselves, so we have to help them. Example 108.4. Okay, it's going to get a little crazier. Ready? All right, we still want to isolate the radical, but our crowd is a little bit more complicated this time. So that's fine. We're going to have to add 3 and subtract x, right? Add 3, subtract x. So we get square root of x minus 1, goodbye, goodbye, equals 3 minus x. I could write this as minus x plus 3. Normally I would do this because I like to keep things in descending order. I like to put my letters before my numbers, right? But I'm going to just leave it like this so that you can see it'll work out either way. This would be my natural preference, but this works equally well. Okay, so now we have to square both sides, right? Same as always. We isolated the radical for step 1. We square away the radical sign here. This side cleans up real nice. Look at the mess we've got over here now. We have to multiply this as a binomial. And P.S., just a reminder, you can't do 9 minus x squared. That doesn't work. You can't do it the easy way when you have a binomial expression and you're squaring the whole darn thing. This is it, folks. I'm sorry. We got to do the dance. 3 times 3 is 9 minus 3x plus x squared. Okay, now I want to change the order that it's written. So I'm going to write, it's 9 minus 6x plus x squared. I'm going to write it in the other order because that just blows my mind too much. Minus 6x plus 9. See, so I took this answer and I wrote the very same values with the very same signs. I just reordered it like that. So Leaving it this way is fine, but now that just feels like lunacy to leave it backwards to me. If we would have multiplied this form of the binomial, we would have gotten this right away. Okay, so now what am I going to do? Well, I'm still going to solve it. I'm going to chase these little leftovers over here. Notice how what started out as the big ugly side has become the simple cute side, and this side that started out simple and cute became uglier. Okay, this all goes away. Now I'm going to write 0 equals x squared minus 7x, right, plus 10. Okay, because I don't really like the way this looks, I would probably flip it. So let's do that. X squared minus 7x plus 10 equals 0. I'm not doing anything to solve this. I'm just rearranging the same equation so it looks the way I like it. All right, now John is going to be nice to us and let us factor these by inspection. This would be x minus 5, x minus 2, right? Because these multiply to positive 10 and add to negative 7. Cute. Okay, oh, we're still going, right? So now we have to solve each of these. Our zero factor theorem tells us that if 0 is the product, then 0 has to be one of the factors. So either x minus 5 equals 0 or x minus 2 equals 0. So x either equals 5 or x equals 2. And then we have to check them both. Oh my gosh. So here's our original expression. It would be square root of 5 minus 1 minus 3 plus 5 equals 0. Okay, 5 minus 1 is 4. Square root of 4 is 2. 2 minus 3 plus 5 equals 0. That does not work. 2 minus 3 is minus 1. Plus 5 is 4 equals 0. No, false. Let me write test here so we remember what we're doing. So 5 is a no-go. But what about 2? All right, let's try that one. 2 minus 1 minus 3 plus 5 equals 0. 2 minus 1 is 1. Square root of 1 is 1. 1 minus 3 plus, oh, not 5. It's plus x. So this should be 2. 1 minus 3 is minus 2. Minus 2 plus 2 is 0. So this one works. So our answer would be only x equals 2. X minus 5 is eliminated. Since we have 2 solutions, since we ended up with a square in it, that makes sense. And it's okay that one works and one doesn't. That's a legitimate result. And so our answer isn't no solution, or the empty set, or the null set. Oh, excuse me. I'm putting myself to sleep. Our answer is just one of the roots. The other one doesn't work. Okay? Last one. Ready? Example 108.5. Solve. Oh, this one looks weird. 2x minus 3. That's the first time we've had a lead coefficient. And look at this. What? We have 2 radicals. That's weird. But they're isolated from each other, aren't they? So we can consider step 1, isolate the radical. We have successfully completed that. We're done. So now, when we square away the sides, we're squaring away both radical signs, aren't we? That's kind of fun. So we get 2x minus 3 equals x plus 2. And all we have to do now is just swim some fish. I'm going to move the x's to the left and the plain numbers to the right. Those cancel. 2x minus 1x equals x. So x equals 5 is our answer. Okay, so now we will test by putting it back into this original equation. So we're gonna get the square root of 5 times 2 minus 3 equals the square root of 5 plus 2. 5 times 2 is 10 minus 3. This would be square root of 7 equals square root of 7. That's true. So this is a valid answer. Yay! I think that the problem before this one is actually easier than this one, because in this one, we had to do a whole lot more, didn't we? So, just because it looks ugly doesn't mean it's harder. I guess that's my advice. But the steps will always work for this. Number 1, isolate the radical. Number 2, square away the radical signs. And then 3, solve using old algebra skills. Okay, yay, that's 108. Goodbye.